In pursuit of transferring technical knowledge and just to gear up the new engineering entrant, myself Pranav is here to deliver today's presentation, Power Transformer Part 73. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with the impact on electrical properties of transformer oil due to oxidation reactions. Transformer aging process is being categorically related to the rate of aging of its entire insulation system, that is cellulose based solid insulation and dielectric oil. Out of the two, the most crucial factor is typically the aging of transformer oil. Important performance index of transformer oil would have to depend on the two electrical properties such as breakdown voltage and dielectric loss. In transformer oil, its breakdown voltage and dielectric loss that are being influenced by the oil's base composition, that is, whether it is of paraffinic based or naphthenic based. However, it has been exhibited that the naphthenic based oils might be of slightly higher breakdown voltages as compared to paraffinic based oils in certain temperature ranges. As this difference is not so much indicative, so there would have shown no significant difference between their electrical properties under the anhydrous condition. During transformer operation, subject variations of oil's electrical properties such as breakdown strength, permittivity, and conductivity all are being strongly influenced if there would have slightest presence of moisture content in transformer oil. All sorts of thermal, electrical, mechanical stresses that would normally have to accelerate the oil oxidation process, causing to degrade its insulating and cooling properties. Oxidation reactions, once started in transformer oil, are spatially impacting on the dielectric strength and increasing the dielectric loss. Most important. With oxidation reactions, it has been exhibited that the electrical conductivity and dielectric losses of transformer oil would have to vary with the dissolved copper ions, hydrogen peroxide, soluble acidity contents of the oil. During oxidation reactions in transformer oil, there would have some polarization losses within the oil, causing to an adverse effect on its dielectric dissipation factor. And that would directly reflect on the overall dielectric losses. However, the intensity of polarization losses would have to depend on the nature of concentration of soluble polar oxidation products and the presence of other factors like moisture and obviously temperature. The event of polarization losses that would start occurring when the oil molecules would have been polarized under the effect of electric field as produced. While this polarization of oil molecules is not been perfectly synchronized with the alternating current field, then there would have some energy dissipation as heat. Concentration of soluble polar oxidation products in transformer oil is to be significantly increased as with the oxidation reaction process progresses, leading to a higher value of the oil's dissipation factor. The dissipation factor is a crucial parameter for evaluating the condition of transformer oil. The dissipation factor is a crucial parameter for evaluating the condition of transformer oil. So, higher be the dissipation factor, which thus to indicate a higher level of dielectric losses and a potential degradation of the oil's insulating properties. Again, I repeat. So, higher be the dissipation factor, which thus to indicate a higher level of dielectric losses and a potential degradation of the oil's insulating properties. The dielectric parameters of the oil would have been further deteriorated, particularly with the rise of temperature. Now, degradation mechanism due to oil oxidation reactions. In an oil field transformer, the oil oxidation process that would therefore significantly impact on the electrical properties of both the insulating oil as well as the cellulose-based paper insulation. Oxidation reactions in transformer oil driven by oxygen and heat would have to create various byproducts, including acids, water, and other polar compounds. The presence of polar molecules in the oxidized oil have thus to allow the oil to be more easily polarized by an applied electric field. Electrical permittivity is a property of material which measures how easily the material can be polarized. Electrical permittivity is a property of a material which measures how easily the material can be polarized. So, the increased ability to polarize of the oxidized oil molecules would thus lead to ensure a higher permittivity value than the original oil molecules. Due to accumulation of these polar byproducts that would cause to create an increased electrical conductivity of the oxidized oil, which in turn affects its dielectric properties. Now let's discuss with the salient points that are to be concluded. There would have a strong correlation between the oil oxidation process and corresponding relative permittivity of oil. Number two, relative permittivity is to indicate the ability to polarize a material subjected to an electric field. Relative permittivity of oil that would tend to increase with having direct influence by the degree of oil oxidation reactions. Electrical conductivity of oil would also have to increase with the level of acidity concentration in oil, which are to be produced during oil oxidation. reaction rather. The electrical conductivity of transformer oil should ideally be as low as possible. The electrical conductivity of transformer oil should ideally be as low as possible. It is as because a low electrical conductivity of oil that would have high dielectric strength, which thus to indicate good insulating properties, and so it would be the most essential criteria for safe and reliable transformer operation. As of the Indian standard specifications such as IS 335-2018 and IS 13631-2018, the electrical conductivity of transformer oil should typically be in the range of 10 to the power minus 14 to 10 to the power minus 12 mho per centimeter, that can also be expressed as Siemens per centimeter or S per centimeter. Oxidation effects on the dielectric constant of transformer oil. Dielectric constant of transformer oil is indeed an essential electrical property as it refers the oil's ability to insulate and prevent electrical breakdown between conductive elements in transformers. Mineral oil-based transformer oil is typically of having dielectric constant ranging from 2.1 to 2.4. And the particular range would generally ensure its effectiveness on using as an insulating fluid, preventing short circuits and providing a convenient pathway for heat dissipation. Dielectric constant of a material is referred as a measure of its ability to store electrical potential energy in an electric field relative to vacuum. It is a simple number or a dimensionless quantity that indicates the relative ratio of the speed of an electric field in a material compared to the speed of the electric field in vacuum. Therefore, the dielectric constant of a material like transformer oil would thus to characterize its ability to reduce the electric field strength within it compared to vacuum. Material with having a higher dielectric constant, which thus to indicate that the molecules of the material can more effectively be polarized in response to an electric field, causing to reduce the electric field strength. For a given applied voltage and of a specific dielectric material with fixed permittivity epsilon, then the electric field strength E is directly proportional to the electric flux density D. Therefore, the relationship that can be expressed by the equation D is directly proportional to E, that is, electric flux density is directly proportional to the electric field strength. Now, D equals to epsilon E, where epsilon is the fixed permittivity of that dielectric material. Therefore, permittivity epsilon equals to D by E, that is electric flux density divided by electric field strength. The permittivity indicates how much electric field is permitted to pass through a material. The electric flux density is therefore be equal to the electric field strength multiplied by the permittivity of the material through which the electric field extends. It has already been exhibited that the molecules of a dielectric material would have become polarized while it is placed in an electric field. The molecules become polarized, which means their electron distribution becomes uneven, creating a partial positive charge on one side and a partial negative charge on the other side. This uneven distribution of charge within the molecule results in a dipole moment, making the molecule polar. Hence, dipole moment is indeed a measure of the separation of positive and negative electrical charges within a molecule, quantifying the overall polarity of a molecule. Again, I repeat, a dipole moment is indeed a measure of the separation of positive and negative electrical charges within a molecule, quantifying the overall polarity of a molecule. If these charge separations within the molecules do not coincide again and still to exist at the same condition, even in the absence of an external electric field, then the molecules are being considered to be in a condition of permanent dipole moment. Again, I repeat, if these charge separations, that is positive, negative, within the molecules do not coincide again and still to exist at the same condition, even in the absence of an external electric field, there is no external electric field, then the molecules are being considered to be in a condition of permanent dipole moment. Molecules having with permanent dipole moment are called polar molecules. Molecules having with permanent dipole moment are called polar molecules. The rate of polarization would thus to quantify how quickly a material's molecular configuration can respond to an electric field by developing an electric dipole moment. Again, I repeat, the rate of polarization would thus to quantify how quickly a material's molecular configuration can respond to an electric field by developing an electric dipole moment. Such response can therefore be characterized by the electrical susceptibility of that material. Such response can therefore be characterized by the electrical susceptibility of that material. Transformer oil is typically being composed of nonpolar molecules, but polar molecules would have been rather introduced through the formation of byproducts during aging and oxidation. As the oxidation products are acids, water, and other byproducts. As of the expression, it can be concluded that the electric flux density of a material does have to depend on its permittivity or its dielectric constant. Therefore, a material with having a higher dielectric constant effectively does to reduce the electric field strength and accordingly reduces the electric flux density for a given applied voltage. A material with having a higher dielectric constant effectively does to reduce the electric field strength and accordingly reduces the electric flux density for a given applied voltage. Basically, a higher dielectric constant means the material can hold more electric flux for a given electric field. Understanding with this relationship, it is clear that increasing the dielectric constant of transformer oil, which leads to a decrease in the electric flux density. Understanding with this relationship, it is clear that increasing the dielectric constant of a transformer oil, which leads to a decrease in the electric flux density. The dielectric constant of transformer oil can also be influenced by the frequency of the applied electric field as well by the the dielectric constant of transformer oil can also be influenced by the frequency of the applied electric field as well as by the variation of temperature as well as by the variation of temperature. Frequency and temperature dependence over dielectric constant. In general, the value of the dielectric constant would have to decrease as the frequency of the applied electric field increases. The technical logic behind this variation is mainly because of the fact that the molecules within the material would have to get less possible time to polarize and align with the rapidly changing field at higher frequencies. At lower frequencies, the dielectric constant of transformer oil would have been much more affected by temperature changes. It is as because while at lower frequencies, the oil molecules have enough time to respond to the changing electric field and their polarization is thus to be greatly influenced by the effect of temperature variation. It has been exhibited that the relative permittivity or dielectric constant of transformer oil, particularly at lower frequencies, is significantly influenced by both moisture content and temperature. As because slightest presence of water molecules in transformer oil would have met to de-escalate the oil's ability to store electrical energy. The relative permittivity or dielectric constant of transformer oil would have been therefore increased with moisture at lower temperature phase. So, under the lower range of frequency where with higher moisture presence and at lower temperature, the oil molecules polarization behavior would have become more pronounced. That is, again I repeat, under the lower range of frequency where the higher moisture presence and at lower temperature, the oil molecules polarization behavior would have become more pronounced rather. This will happen as due to increased dipole alignment and reduced molecular mobility. Hence, it shows that the relative permittivity or dielectric constant of transformer oil, particularly at lower frequencies, increase rapidly with higher moisture content, at of lower temperature. At higher frequencies, the dielectric constant of transformer oil would have become less sensitive to temperature changes. It is as because while at higher frequencies, the oil molecules may not get enough time to fully polarize in response to the rapidly oscillating electric field. As of this consequence, the basic involvement of any variation of temperature on its dielectric constant becomes less significant. The dielectric constant of a material is also being decreased with the increase of temperature. The dielectric constant of a material is also being decreased with the increase of temperature. It is as because the vibration of molecules within the material structure would have to increase with the corresponding rise of temperature, causing to disrupt the alignment of dipole moments under an external electric field. Dipole moment alignment is referred to the tendency of dipoles to align themselves under an external electric or magnetic field. However, depending on the nature and type of transformer oils, as for example mineral oils, synthetic oils, there would have different dielectric constants and temperature dependencies. But it is quite evident that the change in dielectric constant would have been typically more pronounced at higher temperatures compared to the lower temperatures. Oxidation effect. Oxidation in transformer oil that leads to produce acids with some other polar byproducts causing to increase the dielectric constant of the oil. But the dielectric loss factor, which is related to the dielectric constant, is also to increase with the degree of oil oxidation. Oxidation in transformer oil that would primarily have to produce polar molecules like acids and water in oil, which thus to contribute to increase the dielectric loss factor, whereas the overall dielectric constant of the oil would not have to change drastically. Again, I repeat, oxidation in transformer oil that would primarily have to produce polar molecules like acids and water in oil, which thus to contribute to increase the dielectric loss factor, whereas the overall dielectric constant of the oil would not have to change drastically. This twofold impact as due to oxidation reaction in transformer oil has made its overall dielectric relationship much more crucial. The dielectric loss factor of an insulating material is directly related to its electrical conductivity. Though the dielectric materials are known for their insulating properties, but they do inherently exhibit some level of electrical conductivity, especially under high frequency or in high temperature conditions. Dielectric loss would have to start enunciating when a dielectric material is subjected to overcome necessary effect of molecular forces to undergo the simultaneous process of dipole orientation and polarization. Dielectric laws would have to start enunciating when a dielectric material is subjected to overcome necessary effect of molecular forces to undergo the simultaneous process of dipole orientation and polarization. Now, dielectric laws will happen under the influence of an alternating electric field where a part of the electrical energy that has to dissipate as heat due to molecular friction during the process of dipole orientation and polarization. So far, the transformer is concerned, its dielectric loss that would refer to convert a portion of electrical energy into thermal energy, which is then dissipated as heat within the insulating materials, that is, oil and solid insulation, when subjected to an alternating electric field. Cause of this energy conversion is due to the flow of leakage current through the dielectric material within the transformer. The chemical composition and molecular structure of transformer oil are being altered during oxidation reactions, which thus to impose the changes in its dielectric constants. But the changes in other parameters like the dielectric loss factor would generally be more pronounced and noticeable at the time of oxidation rather than changes in the dielectric constant. However, dielectric loss factor or dissipation factor and dielectric constant both are the most important electrical properties of transformer oil, as because these two parameters are much crucial for evaluating the oil's insulating performance and its suitability for using in transformers. The dielectric constant of transformer oil is an intrinsic property of its ability to store electrical energy in an electric field, and it's directly influenced by how readily the molecules within the oil can be polarized by an electric field. As of the consequential effect of oxidation reaction, that would primarily introduce polar molecules into the transformer oil, which have a more significant impact on energy dissipation, that is loss factor, than on the overall ability to store electrical energy, which is called dielectric constant. Let's stop here. Further to be continued at later stage. Thank you. Thank you for listening the video. Kindly do like, share and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section, please. Thank you. Thank you for patient hearing.